I forgot to go back and make that automatic. Okay, so yeah, we'll be working off this more sample amps on PolyLearn. And can you see this okay? It's kind of light. The lines are kind of light.
Yeah, I can see it. Okay.
Okay. So these are taken right off of data sheets. So these are amplifiers made by professionals in industry making better money than I am. But these are actual professional. If you buy like an amplifier, like an op amp off the shelf, these are what's inside of them. So let's look at the first one. Is everybody able to find the handout? Okay, so actually, can I make it bigger? I don't think I can make it too much bigger. Oh, so close. How about this? Let me try something. This may just wreck it. Let's try shrinking it a touch.
At least I can see it pretty okay. Not now, but before.
Okay.
Oh, I don't know why it became like super blurry all of a sudden, but I could still read it, like
Okay.
the words.
All right. Yeah. Don't know how to get rid of. Oh, there we go. Ah. Okay, then I didn't need to do that. All righty. So let's talk about just a few symbols on this diagram. Anybody know what the two circles are?
Current source?
Current source. Yeah, so we've been using the kind of the traditional the traditional current source like this, but this is a current source right here. So that is shorthand for what? Think Lab 2.
Current mirror?
Current mirror. Yeah, so this is just shorthand. It's just trying to make the schematic a little prettier. What are these squares? That's not very good. But
Are they just resistors?
they're just resistors. So the squares are resistors. Okay. What's this diode right here? What's it probably? How's it implemented probably?
Would be to block current, to have current going in one direction.
Okay, has current going in one direction, but as a component, how do you think that's probably implemented?
Is it just dropping voltage so that we can bias that other transistor, right?
Spencer, your picture freaks me out. Okay.
I'm sorry.
No. It's just fine. It's kind of interesting having your voice come out of her face. Yeah. So it is a voltage drop. So it could also be drawn as a battery. Could be drawn as a battery. You'll see that in some schematics. How do you implement that though?
Is that what we did in one of our labs for the dead zone that we were trying to avoid?
Yeah, that's how you biased to get rid of. Anybody remember what that's called? Or what the circuit was?
Push pull?
Push pull. Okay. And then you had to shift up and down by VB on. You needed to get 2 VB on between the two transistors in the push pull. And you level shifted. What did you use for a level shifter?
Common collector?
Exactly. Okay, so you used a common collector. So this diode if it was kind of drawn a little differently. This could be a common collector, but there's another way to get that VBE on drop, and that is just to diode connect a transistor. And then because this is about VBE on, this will also be about VBE on. But sometimes in diagrams, in circuit diagrams, you'll see that drawn as a diode, sometimes as like a battery, sometimes as a voltage source, but all those mean the same thing. It's probably a diode connected transistor. And that's one reason I kind of like this diagram. They've cleaned it up so you don't have to worry about too many of the details and you can still see how the amplifier works. Okay, are there any other parts that you see that you haven't seen before? I think everything else should be good. And this is kind of your VCC. This would be your ground or your -5 volts if you're doing dual rail. Okay, so first thing when you're trying to figure out what an amplifier does, first thing is to break it up into stages. We could go any direction, but let's start from the input. So I see an input, I see two inputs here. What circuit do you see there? So what stage, I should say?
Input stage.
Input stage, and how's it implemented?
Differential pair.
Differential pair, okay. So let's figure out what's inside that differential pair. So is the differential pair just these two transistors?
Current source too.
Okay, so is it just the current source in these two transistors?
The load as well.
And the load's down here. So that if you're drawing a circle around the whole diff pair, it's this entire thing. You have to include the loads, you have to include the input transistors, and you have to include the current source. Okay, what's kind of basically different than the diff pair that we've been looking at?
They use PNP.
PNPs. Yeah, it's a flipped version of it. This is a hard question, but can you think of a reason? You see quite a few op amps that use PNP, a flipped version of the diff pair on the input stage. Any idea why? And think about the job, what an input stage's job is.
PNPs don't have better gain, do they? Or am I getting it backwards?
They're probably not going to give you, I won't say that. I won't say that. What's the drawback of using a P-type material as opposed to an N-type material?
You have to like set up wells for it in the substrate, right?
Okay, so if you're fabricating it, it costs you extra money. What else is just kind of intrinsically about P-type material and N-type material?
It needs like negative voltage values to turn on.
Okay, so you have to remember to flip the voltages.
Speed could be an issue due to mobility.
You get
Mobility.
body diodes too, right?
Mobility, that's the big word. So if it has lower mobility, what do you think its resistance looks like?
Larger.
Larger, and what's the ideal input stage? What's its job?
To have a larger RN.
Higher.
Yeah, so PNPs actually give you a little bit higher RN usually. And so might as well flip it and get that little extra bonus. But the reason why I was not giving you an answer on whether gains better. They conduct less current, but they have higher resistance. So if you're using an active load, PNP, it probably looks like a bigger resistor than if you used an NPN. So less current would give you the same gain. They're going to conduct less current, but because the resistance looks bigger, they might balance each other out. So I don't have an answer for that. I think it's case by case. You have to go and look at the model file and see what the characteristics of each transistor is. Okay. Okay. All right. Let's ignore this little buffer here for a second. We'll come back to that. Let's put parentheses around it. We'll put parentheses around it. We're kind of ignoring it and just assuming that this wire goes straight to there. Let's just ignore that amplifier and just assume it's connected straight from the output here to that node. Okay. Next question is, what's the next stage?
Gain stage.
Gain stage. Okay. Now this is tricky. This is also tough to see. What is in the gain stage? What is the gain stage made up of? What parts are put together to make the gain stage here? So first of all, what kind of amplifier? Do we want to find the parts first? Let's try to figure out what kind of amplifier it is, and then if that doesn't work, we'll try to go back and figure out what the parts are. So this is the output of your input stage that's connected here. So it's connected to the base of this transistor. Okay, I'll leave it from there. Oh, wait. I take it back about the gain stage. Usually it's a gain stage, but the question is this a gain stage or not?
No.
No. Okay, what is it? What is this? What's the next circuit it hits? This last stage here, you can kind of see it's a push-pull. And you can see this is going to one transistor of the push-pull. This is going to the other transistor of the push-pull. So I consider this a little bit hard to see, but I consider this one of the inputs to the push-pull. So I consider this kind of the output of whatever this stage is. Let's open it up. There's only 6 possibilities. So what do you think the middle stage is?
Is it a phase inverter? So you can drive both sides of the push-pull?
It's not, I wouldn't call it a phase inverter.
I'm stumped.
Okay, so let's go back to this transistor. I think that this is coming from the diff pair. That's kind of, you can see that. So it's not a common base. Which terminal is the output kind of connected to?
Collector.
Is it the
emitter?
collector? The emitter, yeah, because this is a flip. This is a PNP down here. So that's always something to check, whether it's an NPN or a PNP. So this is a PNP, so the outputs on the emitter and let me say one thing about this diode. It's a DC voltage source. What do you do to DC voltage sources when you do small signal analysis?
You ground them.
You ground them. So if you're trying to figure out what this is and you see something like this, a DC shift, you can just assume that it's not there. You can assume that that wire is just kind of, there's a short across that DC source. Does that help at all? Okay. So input on the base, output on the emitter. So what kind of amplifier is this?
It's common collector.
It's a common collector. Okay, well that's weird. Why would you have a gain of 1 in the middle of your amplifier?
Maybe you're okay with the gain that you have. You just want to lower the output resistance.
Okay, this isn't quite going to the output yet. It's going to the push-pull.
Is
we'll
it
talk
acting
about.
as a buffer between the two?
Yeah, but why would you need a buffer? Exactly.
It's for crossover distortion, right? That's why you have that second diode.
That's why the diode's there, but not the common collector. If you have two circuits and you connect them together and they stop working, so you have two circuits that work great and then you connect them together and they stop working, what's probably the problem?
Oh, loading?
Loading. Exactly. So whoever designed this tried to connect the diff pair up to the output stage and it failed. He said, well, shoot, we have to do something here. And what's the characteristics of a common collector?
High input resistance, low output resistance.
Yeah. So if this was pulling current, now it can pull current from the common collector, and the common collector won't pull current from your diff pair, so it'll protect the diff pair. It might just be there for the shift, but so let's try to circle the common collector. What are the parts of the common collector? If you had to circle the whole thing.
Would it be that transistor that we were working with and
Okay.
the diode too?
Okay, so got the diode, which ends up as short if you're doing small signal analysis. What else? What other part of a common collector do you usually have?
You usually have a load at the emitter.
Yeah, it's not usually called a load. It's actually, but yeah. So, what's this?
Oh. It's a current source, so like large resistor.
Yes, exactly. So just like you had an active load for a common emitter, this is acting as a current source for the common collector. And we haven't, let's get a different color here. Let's go back to black. Okay, so for a common collector, on the last homework you did a touchy-feely problem. And you saw that if V in goes up, V out goes up. Now you've got more current across your resistor, which means your VBE goes up and your V out goes down, back down a little bit. So because the current changes, your gain of your common collector is less than 1. So that's on the homework if anybody's not there yet. But what happens is your V in goes up and your V out goes up. And then because the current goes up, the VBE of your transistor has to go up and this goes down a little bit. Okay. But if you had constant current, I mean, that the VBE right here changes because when V out goes up, the current through the resistor changes. But if you had a ideal current source, now no matter what happens to V out, your current is constant, so your VBE stays constant. And now your V in and V out follow each other really well. The one on the homework had a resistor, so when you changed V out, the current changed and your VBE changed. But if you have a current source, it follows really well. Now the gain is probably almost 1. Okay, I can't tell if that made sense. Anybody give me a thumbs up on that? Is that okay? Okay. Okay. All right. So yes, this right here is this circuit right here, but flipped. And you get to ignore, this is just a battery. It's just putting a VB on drop across there. That's a DC voltage. So both sides are moving, both sides of that diode are moving together. And it's like it's not there. So the whole thing is you need the resistor, the thing that's behaving as your resistor. You need the transistor. The diode is for the push-pull. It's not part of common collector, but that's a common collector stage right there.
Professor, why was it that we needed that again? Or like, what was the advantage of putting that there?
It's either, there's 2 possible reasons. It could just be there to get the difference in the base voltages here that the push-pull needs. Or it could be because when they directly connected up this output stage to the diff pair, that the output stage was loading the diff pair.
So does that mean that it needed more current? Is that what?
It means that this stage was pulling so much current, it was messing up the diff pair.
Okay.
Okay.
And so because we have like a large RN for the common collector, that's not an issue anymore?
Yes.
Okay. Thank you.
Right. Then questions on the push-pull stage. There's something odd going on here, but ignore that for a second. Just look at this transistor, this resistor, and this transistor. That's your push-pull right here. So the resistors are very small. So let's even ignore them. So what voltage do you need between the 2 bases here for a push-pull output stage?
Uh, 2 VB on.
2 VB on. Does this give you 2 VB on between those 2 bases? In other words, does this have crossover distortion or does it not have crossover distortion?
It does, right? Because of the resistor?
You can ignore these. Go ahead and ignore those. Those are just for protection.
Okay. Then I would think it wouldn't have it.
Well, let's see. Let's follow this path. Let's go this way. So let's say this is some voltage. If this is a diode connected transistor, what's the drop across here?
0.7.
Okay, so whatever your VB on is, so you've dropped 1 VB on. Okay, then you come down here. What's the voltage from here to here?
Another VB on.
Another VB on. So from here, you dropped 1 VB on, 2 VB ons, and that's the wire that goes to the base of the second transistor. So there actually is 2 VB on there. It's kind of hidden. So it looks like, oh, there's just 1 drop here, but there's actually a second one through the common collector. Okay, so we've got our 2 VB on. So do we have crossover distortion or not? What do you think?
Don't, because we have the 2 VBE on.
Exactly. Because we have 2 VB on, we're good. And the way to figure out what voltage you need is if you follow the push-pull from this base to here, that's 1 VB on drop. If you're ignoring the resistors, then you have a second VB on drop. So that the drop across here to put both of these on the edge of conduction, that has to be the same as the drop going this way. So the loop this way and the loop this way should have the same drops in voltages. And then you won't have crossover distortion anymore. Okay, so did green, kind of, should we do purple? So this is actually the push-pull. Okay, here's another question for you. I guess I'll do that in blue. There's something going on here with this resistor. There's something going on there. Why? Anybody know why that resistor is there? And I'll tell you that it protects the circuit. And what hurts circuits?
Current.
Current. Okay. So something's going on with, I'll draw it out in blue. This transistor and this resistor.
I mean, is it like limiting the current through the base?
Exactly. But which base?
The base of that NPN that's blue.
This one?
Oh,
Actually,
never mind.
okay.
Is it the other? Oh wait.
Let's call this Q1. This, I don't know, Q, because there's not very much space.
Oh, is it limited? Oh, the current through the base of that, the one near the output. Is
Yeah, it's limiting this one, but why?
Is it? I'm probably doing this all wrong, but like, is it because of the current source there?
No, it's pretty self-contained in the blue circuitry there. And the current that you're worried about is the current through the push-pull. So when that gets too big, this thing helps in some way.
Is it some form of degeneration for that pair?
It's not degeneration. It's think simpler.
Does it just decrease the voltage drop across that resistor, that one highlighted in blue? Because
It is the voltage drop, but when there's too much current, are you decreasing?
You're increasing the voltage on the node after that resistor.
Yes. So the voltage across here, when there's lots of current, what happens to that voltage?
It gets bigger across.
It gets big. Is anybody seeing it? Seeing what happens?
Does Q limit the voltage across the resistor, like with the VBE on?
The VB on comes into it. You're almost there. If there's a little bit of current, then this will be a pretty small voltage. And will Q be on? Will Q be conducting?
No.
No. Yeah, if there's only a little bit of current here, then you have a small voltage drop across the resistor, and this VBE will be less than VBE on. What happens if all of a sudden, for some reason, you've got giant current going through the push-pull? What happens to the voltage across this resistor?
Gets really big.
Gets big, and then what happens to Q?
It turns on.
It turns on. And where does it get its current from?
The current flowing through the base that's going into Q1.
Exactly. So now, instead of all this current going through Q1, it gets split, and some of it gets pulled off of here and gets dumped onto the output. Instead of going into the base of Q1, it gets bled off and thrown out.
Okay, but then wouldn't there still be like it still gets split and the current going through Q1, wouldn't that still, or the point is that we're decreasing current. It doesn't matter that there's a big voltage going into that node, right? With after the resistor. That's why. Because I was wondering, like, there's still current going through Q1, but then it's just smaller.
Yes.
And, okay.
Yeah, you're just turning down the current through the push-pull.
Okay. But okay, I see.
Okay. Questions? I see some questioning faces. Kind of. Everybody turned video.
I'm very confused about it.
Okay.
I don't know. I'm really bad at labs. I don't know what's going on usually.
So think of beta. Beta is the current into the base times beta. That gives you the current going through your transistor. So if you could turn down the base current, the current through that transistor will get smaller.
Oh, okay, yeah, that makes sense.
Okay. So originally, if you had some big current going through there, and induced a gigantic current going through there, but if there's a gigantic current, this voltage goes up, this transistor turns on, and it steals some of that current to go this way instead of into the base.
Okay.
It clicked for me that time.
Okay.
Round like 4.
Tina.
Okay. Uh-huh.
What keeps, like, let's say for whatever reason Q1 is drawing a lot of current into the base. What's keeping that current from coming from the like the current source directly instead of coming from the Q? I guess, is that current that's getting pulled away through that tiny Q transistor necessarily coming from the current that would have gone into Q1, or is that Q1 current, like, it could still be getting pulled?
Okay. Yeah. Good question. This current right here is split between the two. This thing right here, there may be some other circuitry on here to make sure it has kind of a constant current. That's not a, let's see, what's the best way to say this? You can assume that this is all the current that's available for these two branches, and you can assume that this one is not perfectly constant, but relatively constant. So whatever current's coming through here, and I'm saying that there's probably a little bit extra circuitry here to keep this current relatively constant. Whatever this current is minus this, that's generally what's coming off of here. And either it all goes into the base or you pull some of it off. Either it all goes into the base. If this transistor wasn't there, it would all go into the base. But this one just says, oh, if too much ends up going into the base, then I'm going to pull some of that off, redirect it. I don't think did that satisfy you? It didn't satisfy me.
No, I mean, I guess not knowing why that current through the common collector is constant is unsatisfying, but I can I take your word for it.
Okay. This, as a common collector, they're always conducting. So you'll always have some current through there. But even if all of the current was going through. Let me come back with a better answer. Let me put it on my. Okay. But this is a pretty common. I'll come back. I'll try to find a better answer for you. This is a pretty common safety structure that you see in output stages. If you notice, it doesn't have that over here. It doesn't have one on the bottom, and I don't know why that is. This circuitry right here, this is a little bit different, and we'll ignore it for now. But are you okay with a diff pair, the common collector, and the push-pull with the safety circuitry? Maybe?
I think so.
Okay. Right. Now this, again, this is done by professional analog designers. And I think you could do just as well. Okay, let's start this one. So what's a good place to start? What do you always want to do first?
The input.
Okay. Yeah, you want to divide it into stages. So you need the input stage. And what makes up the input stage here?
See a current mirror at the bottom, and then there's a current source at the top. So I would think that whole like first from the current source to the current mirror.
Okay.
Right.
What about these transistors?
Are those like Darlington pair?
Exactly. Exactly. So those are replacing a single transistor, so they get circled. And for every stage, you want to go from rail to rail, so supply to ground. If you don't go all the way from the top rail to the bottom rail, you haven't got the whole stage. Okay. First thing to notice on this input stage, what's different than the diff pairs you've been working with? Same thing as the last one. What's a sneaky way to get a little higher RN?
Use PNPs.
Use PNPs. So this one's also flipped. And now you have a different symbol for a current source, and that's why it's good to know all the different symbols. But this is probably a current mirror. But yeah, that was a good place to zoom in on. This Q1 and Q2 and the Q3 and Q4. Again, what are those?
Do you mean like what's their configuration?
Yeah, you already said it.
Darlington pair, yeah.
It's the Darlington pair. So why would you want those on an input stage?
Better through current?
Better what?
Through current?
Okay. Could be, it could give you more current.
Really high RN.
Super high RN. Do you remember the RN for a Darlington pair? So let's see if my pen's working today. Darlington pair. Oh, yay. Okay. Oh, stopped already. Okay. Darlington pair. Okay. Do you remember the RN for a Darlington pair?
It's like the like R pi 1 plus like R pi 2 times 1 plus beta.
Yes. So Q1 has a resistance it sees on its emitter, and that's just the input resistance of Q2. So the input resistance of Q2 is acting like that RE that you see with degenerated transistors. So the RE, usually in your equation you see an RE here, but in this case it's the input resistance to Q2, which is the resistance on the emitter, not a resistor of size RE. Okay, so that's super gigantic RN. That's exactly what you want for your input stage. That's, while we're here, we have 7 minutes. Okay, 2 things to talk about here. Over in this other branch, it has like 100 microamps of current, and this has, is that milliamps or microamps? I can't read it.
Looks like micro.
Okay, everything else is micro, isn't it? Yeah.
Yeah.
So this is a small current compared to this current. Why might you want a small current in the diff pair?
Because you know that the Darlington pair will give you a lot of current. So, because it's like beta times more.
Yeah, it will. So any current, this thing can provide current. It's actually uses, yeah, this can supply a lot of current, but if this was connected here, it would be even more. But it has something to do with this Rn still. So that's the hint. Why do you think you use less current in the diff pair than you do over here in the gain stage?
Maybe because the RN is so big that you only need to work with smaller currents, like in terms of the voltage being observed.
Okay. It's true that you only need a small amount of current here, probably. But what else does current? Here's an odd question. Does current show up in this equation?
No.
Does it? So it doesn't directly show up. Does it indirectly show up?
With beta, yes.
Okay. Beta, yes, but beta won't. It does change a little bit, but it won't change. If you change your current, beta doesn't change. So beta's pretty constant. That leaves. Now, what's the equation for R pi?
Beta times the VT over the collector current.
So what happens if you make the collector current really small?
You get a big R pi.
Get a big R pi, and that makes this Rn even bigger. So if this is 100 times the current, if you used 100 microamps over here, let's see, that's 1/6. You'd have 1/16. You'd have 1/16 of the Rn, because both of these are pi's. Would they both? At least the R2, R pi 2, would be 1/16 smaller. Instead of using 6 microamps, if you used 100 microamps, then this R pi would be much smaller. Even though you're multiplying it by 100 or 200 or something, you'd be multiplying a much smaller number by that. So using a small current here gives you a big Rn, even bigger Rn.
What's the lower bound for how much, like, how small of a current you can have there?
Okay. Current's kind of a trade-off, because if you have a very small current, as soon as something wants a little bit of that current, like this over here, what's this next stage right here? What's the second stage here? Ignore the diodes for a little bit and the capacitor. Common collector. Yes, so you have the input, the signal coming from the diff pair, that's on the base. and then the output is on the emitter. So what's left is the collector. So this is common collector. So this probably, I can almost guarantee that this was being loaded by your gain stage. So they needed to protect it. And part of the reason it was so easy to load probably was because that there's so little current going through here that even if a little bit gets stolen, then it just messes up the diff pair. Okay. But we'll go on to those on Friday. Today's Wednesday, right? I think I got that right. Okay. This last part right here, I don't know if I can do it exactly in a minute, but let's give it a try. It's going to take me that long just to draw it. Plus in minus out plus. Still hasn't turned to 3 o'clock yet. Let's go through this really quickly and then you can think about it another time. Okay, so let's say I increase VI plus. This is, I think I had this in the lab handout, right? Oh, it's 3. If, we'll do this next time then. But this diode connection right here, this actually increases your gain on V out plus. So it looks like it's a current mirror, but it's not actually. It's doing something with that, with an active load right here that actually makes the gain of this stage bigger. We'll look at that next time. So every day for the next few days, we'll go through one of these. And this one went really slow. I mean, the first one up here went really slow, but you'll get faster and faster. And we'll see a few more structures that you see in op-amps as we go through them. Any questions on the circuits for today?
Professor, are you gonna post like this annotated version?
Sure.
Okay, that'd be awesome. Thank you.
Okay. Anything else? All right. All right, that's all I got.
Thanks, Professor.
All right, see you later.
Thank you.
Thanks, Professor.
All right, bye-bye.
Thank you.
Bye.
Professor?
Mm-hmm.
I had a quick question on the homework.
Okay.
Part K of the number 2, when it asks to calculate the PSRR, sorry.
Okay.
So the last time we looked at PSRR, we looked at the resistances, like when we switched the VN from the to the emitter, right? Yeah. So in this case, like, are we supposed to, because I know the ADM is at the top for the AV gain, but for the bottom part, are we supposed to calculate this using like small signal model, or is it something we do like on LT Spice?
This is if you think through this one, let's see. Let's draw that out. Should I try and see if my pen's working again? Ah, it is. I think I need to bring it to a therapist. I don't understand how it thinks. Okay, and again, on all these metrics, if making VI plus equal to VI minus makes the problem easier, then do it.
Okay.
So if this is V out plus, V out minus, and so if you make VI plus equal VI minus, then what do you know about the currents through the two sides again?
They would be ISS over 2.
ISS over 2. You have it on both sides. Now, again, just like with the common emitter, you can set these to a DC voltage, so just setting it to something randomly,
Mm-hmm.
and then you move the supply.
Mm-hmm.
Let's make them prettier colors. So you move the supply. Do you remember the equation for V out plus? Call this VCC.
No.
Okay, we've got the current, and let's call these R.
Oh, so just VCC minus R times ISS over 2.
And remember, the VI and V plus don't, the VI minus and VI plus don't change. So the current never changes.
Mm-hmm.
So the question is, what happens when, how much does V out move when VCC changes? Wow, these glasses look funky. I never look at myself.
Well, wouldn't they move a lot? Or like, because when you say move VCC, like changing the voltage, right? Like, so they would be moving a lot, assuming the resistor is like, or if the resistor was.
Let's do this. So the first, if VI plus equals VI minus equals 3 volts, and we're just leaving it there, that's our value on V out. And then let's say I change VCC. There's a little bit of noise. Let's assume a little bit of a noise, and it moves delta V. What's your new V out value?
It would be VCC plus delta V minus R ISS over 2.
Yes. And if you do that subtraction, you just get delta V. So this is how much, that's how much V out moves when, should continue this down here. And in this case, delta V is considered your V in for noise.
Mm-hmm. Oh.
And this is considered your V out for the whole circuit and for noise. So what's the gain there?
Wouldn't it just be the VCC plus delta V over, or delta V out over V in? So
Or the change in V out over the change in V in.
Change in V out over the change in V in. So it would be delta V over that VCC over, or VCC plus delta V.
Okay, but VCC doesn't change. So
just 1?
Yes. That's your change in your V out. That's how much your V out changed when you changed V in by that much. So you just get 1.
Huh. Okay. So then that would go on the denominator of our PSRR calculation.
Yes.
So we do the same. So it's just the ADM?
Yes. In the numerator, yes. Oh, and divided by 1, so yes.
Yeah. Oh, interesting. Okay.
Which isn't, I mean, it's not bad, but it's not great. If whatever noise you have on the supply shows up exactly on your output. It's not as bad as, the common emitter is the worst circuit there is for noise on the supplies. So it's just better, but
Okay.
still not perfect.
All right. Thanks, Professor.
Okay, wherever the thing is.
That makes a lot more sense.
Right. Did anybody else have questions on that one? Oh no. Oh, I see. It didn't scroll. How are you all? Are any of you going to the banquet?
We have to sign up for that, don't we?
Yeah, I think you have to directly write to Yvonne now. I think they have like 150 people signed up. So
Oh wow.
yeah.
Well, maybe.
Maybe. Do you want to see the? Oh, wait, it's already 10 after. Never mind. I was going to offer to show you the video so far, but there's some missing. A few people didn't send me videos, so I have some holes. I think some people will send me some later today.
Well, if there's time on, I would say I would like to watch it maybe after class, but
Okay.
I've got a midterm right after, so maybe on Friday. If I don't get to go to the banquet, I'll ask.
Absolutely. Somebody said, put a link to it on, not PolyLearn, Canvas. I think I have to say PolyLearn before I can remember Canvas. It seems to be how my brain works these days. Okay, so homework, I guess get it in tonight or tomorrow, and the midterm isn't quite finished because I keep doing that video because the video's more fun. And then you'll have like a week to do the fake midterm as homework, and then I'll post the solutions, and then we'll set up times to meet during the 9th week or something, talk about it. Okay. Any other business? Really small group today. Casey's not here. You're
He'll be
the
here in a second.
okay. You're the spy. Okay.
Yeah.
Okay. Then today, I like doing this. It was when it's face to face. I started doing this a few times ago in 308, and I always have fun, but it's hard to do when I can't see people's faces on this. So we'll give it a try. It wasn't as lively as it usually is in usual classes, but if you go on to Canvas and go down to week 7, there's down here, I'm sharing, right? There's more sample amps, spring 2020. That's the handout that I'm going to be working off of today. Okay. Do y'all find that okay? Okay. All right, so that's what I'm working off of today. And the first amplifier on the sheet is this one. These are taken off of data sheets. So these are amplifiers designed by professional people getting paid a lot of money because they're analog designers. And these are actually products that you can buy through DigiKey. So just before we start going through here, no, I'm already on a narrow line. Let's have to move you all over. There we go. Let's look at a few of these symbols. So there's this symbol right here. What's that?
Isn't that a current source?
The
Or
current
sink, I guess.
Okay. Source in this case because it's providing. Okay. Yeah. So it's exactly what we've been drawing as that symbol. Okay. What about the squares? What about these squares? Oh, this is much better.
They just represent an impedance.
Impedance. Yeah, in this case, it's usually resistors in these, but impedance is probably a better answer. I'll draw it as a resistor just because. Okay. Then there's this diode over here. This is so much better. Why didn't I do this in the last class? I was trying to draw these when my pen wasn't working again, so I was trying to draw them with the mouse. What do you think that is? There's a lot of shorthands in this particular schematic. It's like the current source and the resistor. So there's a lot of shorthands, but what do you think that, how is that implemented? Oh, actually, let me give you the other shorthand. What is this current source actually in the actual circuitry that's on the chip? What do you think it is?
Current mirror.
Current mirror. So it is actually, no pen? It is actually this whole thing. It's representing this whole thing. Diode connection. And where that's, if this is your current, and this is your current, then this is your current right here. Doesn't look good. Okay, so again, back down to the diode. How do you think that's implemented on an actual circuit? Probably.
A diode connected transistor?
Exactly. So if you're dealing with an NPN down here, it's this. And because this is about VBE on, and these two are shorted, this is also about VBE on. There's some other ways to draw that. You see this drawn sometimes as a voltage source. Sometimes you see it drawn as a battery. But they generally just represent a DC voltage drop. Okay, so those are all the symbols. I think everything else you're good for. They're just transistors and kind of a, this is an amplifier, but we're going to ignore it today. We're going to pretend like this doesn't exist. Just get rid of it. Let's get rid of this wire too. Let's assume that's just connected up like that. Okay, so first thing, when this is because of all the shorthands, and I'm sure there's other circuitry in there that they've removed to make it look pretty. So the schematic looks pretty simple. So this is a good one to practice on. But what you usually want to do when you're trying to figure out one of these more complicated circuits, and they'll get more complicated pretty quick, is circle the stages, or at least figure out where the stages are. And for us, we've been dealing with a really traditional 3-stage amplifier. But depending on what these amplifiers are for, they may vary from that traditional 3-stage amplifier design. So first question is, where's the first stage on this? What's the first stage? And you could go in any order. You could go in any order, but let's start from the input for this. Oops. So starting from the input, what do you see first?
A diff pair.
Okay, diff pair. And what's kind of the basic difference between that diff pair and the diff pairs you've been working with? It's maybe too basic a question, but.
Uses a current source instead of a sink.
Okay, and what's that mean about the entire circuit?
It switches to PNPs instead of NPNs.
Exactly. So it's a flipped circuit. And there you see PNPs as the first stage of an op-amp quite often. Can you think of a reason you might want to use a PNP-based diff pair rather than an NPN-based diff pair? Think of any reason?
Don't PNPs usually have a smaller beta value?
Okay.
I'm not really sure why that would help, but that's all.
It's the right place. That means the current's less. If the
Your VP on.
okay, what do you like in an input stage? What's your ideal input stage?
Really high in RN.
Yes. So if something's conducting less for the same voltage, then it's going to look like a bigger resistor. So PNPs, their mobility is a little bit lower. They conduct less, and so sometimes, not always, but sometimes they show a bigger resistance. So that might be one advantage of using the PNPs here. Let's make sure we know exactly where the diff pair is. What if I was going to circle all of the diff pair? What would I circle?
Both of the PNPs, both of the resistors, and the current source.
Exactly. Yeah, you have to go all the way from one rail all the way down. If it's a stage, it's going all the way from the top rail to the bottom rail. And this diff pair right here, without the loads, it's not going to generate a voltage. It can generate a current. Without this current source, then you can't steer the current. So you need all 5 of these parts. You need the current source, the 2 input transistors, and the 2 resistors. Okay. All right. Okay. So any questions on the diff pair stage? Okay. So let's see. What's the next stage? And this is really tricky. This is a bit tricky.
The gain stage, and it looks like it includes the current source and the diode and that PNP.
Yes, but is it a gain stage? What kind of amplifier is this? So I'll circle everything that you just told me. That's exactly where the stage is. Circle that up, all up. Goes rail to rail. So it's a complete stage. So the input to the stage, it's coming in here, and it hits the base. So it's not a common base. Where's the output of that stage?
Is it above that diode?
It's above the diode, so it's on the emitter side of that transistor. So it's not a common emitter.
So then you have a common collector.
Yes. Okay. When do you use a common collector? Why would it show up in the middle of this circuit? Usually that's a gain stage right there. And there's 2 reasons.
Is one of the reasons that it's acting as a buffer?
Okay, and what are the characteristics of a buffer?
They don't draw current, and they supply a lot of current.
Exactly. So maybe they took this diff pair and connected it up to the next circuitry, and it stopped giving as much gain as it did before. Something happened. So yeah, this could be protecting the diff pair from the next circuitry. Let's come back to the second reason. So one reason for this might be buffer. Could be. I'll write could be, because the other reason is just as possible. Could be a buffer. So protecting the diff pair from the next circuitry. We'll come back to number 2 in a minute. Let's go on to the next stage. What do you see? What do you see in the next stage? And if the rest of you want to join in, that's good too. Let's name some of these. No pen. Let's call this. We'll call this Q1, and then this transistor here, we'll call that Q2.
Is it a push-pull output stage?
Exactly. Yes. Okay. And which transistors, if this Q1 is going to that, that's Q3, which transistors make up the push-pull stage?
Q1 and Q3.
Q1 and Q3. And it has to go rail to rail for it to be considered a whole stage. So those resistors right there, we can talk about them in a minute. Okay, push-pull output stage. Okay. So for a push-pull output stage, to figure out the voltage that you need between the two bases, you can travel inside the push-pull from the base of the top one to the base of the bottom one. So if I go from here to here, how much voltage, how much has the voltage changed?
About VBE on.
About VB on. And let's ignore the resistors. They should be very small. And then you get down here, and then I go from here to here. This is if you're ignoring the resistors, this is VB on below the base of Q1. So now you're here. This is a VB on below the base of Q1. If you go to this node, what is this voltage compared to this voltage?
Another VB on lower.
Another VB on. So what's the net difference between the base of Q1 and the base of Q3?
2 VBE on.
2 VB on. So that's the voltage that you need to bias. That's the voltage you have to set on the bases for this not to have. What are you trying to avoid when you set it 2 VB on across apart? Should we do the sound game? It looks like it's on the edge of your tongue, tip of your tongue. I'm starting to sound like a Trump. So we'll try it.
Crossover.
Yes, crossover.
Dead zone or
distortion.
Distortion.
Distortion. Oh, yeah, I don't know why the crossover, the sound game hasn't become more popular, but yes, crossover distortion. So if you follow this path from the base of Q1 through the push-pull to the other base, that is the voltage you need, so you won't get crossover distortion. So no cross. If you want to get rid of crossover distortion, you travel inside. Since I don't have my pen, I won't write the whole thing, but travel E of Q1 to B of Q2 or Q3, and that's the voltage that you need. So here's my question. So that is the voltage you need to not have crossover distortion. In other words, that flat part where it goes loop, flat, flat. Does this have 2 VB on between the base of Q1 and the base of Q3?
Doesn't it only have one VBE on?
Okay, that's usually the first response.
Or is it 3?
Well, let's travel. So let's go this way. So if I go from here to here, what's the approximate voltage drop across the diode?
VBE on.
Okay, so you've got 1 VB on drop. Let's keep going down. You're trying to get to the base here. So you go down here, and then you're not directly connected to the base. So you go down here. What's the drop across here?
VBE on.
Okay, so you've dropped 1 across the diode and then another one across here, and that's actually the second base voltage. So even though there's only 1 diode, so it looks like there's only 1 diode drop, this center stage here, the common collector, that shifts it down another VB on, so you have 2 VB on between the bases. Okay, so that's the other reason for this common collector. It could be only, could be for biasing. We'll call it biasing. Sorry, I'm so slow. Of push-pull, call it PP, push-pull. Okay. All right. So one more thing to look at here. We find, what color have I not used? Like orange or something? Okay. There's something going on here between this transistor, this resistor, and that resistor. I guess just those 2 parts. I'll tell you that this is safety circuitry. I know like degeneration was considered, protects your circuit. This is another often seen safety circuit. And when I talk about safety, that means you're protecting the circuit and you from something. What's the thing that hurts you? Current. Okay. So how does that work? And I'll tell you, it's protecting against too much current through the push-pull.
So if you've got too much current going through the emitter of the top push-pull, it's going to increase the current going through the orange transistor, and it'll
orange
or through Q2.
Will it though directly? It does, but is it directly doing that?
Well, because the voltage across the resistor.
There, yeah. Or that's where the camera is, yes. So I agree. If there's too much current through the push-pull, then what happens to the voltage across the resistor? You already said it, but.
Well, it would go up.
go up. So now you have a bigger voltage across that resistor. What's that do to Q2?
Does it turn it on?
Exactly. Yeah, so if this is a pretty small resistor, if there's a small amount of current across here, if this is well designed, then you won't have VB on across this resistor. If it's a normal amount of current, then the voltage across the resistor will be less than VB on. And notice that the voltage across the resistor is VB on of Q2. Okay. Then when a lot of current goes through, what happens to the voltage across the resistor? Goes up. And then when the voltage across this resistor gets to be above VB on, remember that voltage across the resistor is just the VBE of this transistor. It turns it on, and it actually steals current from the base of Q1. It lets current go this way and gets dumped out the output, or sometimes they have another path down here for current. But yeah, whatever current was going to the base, now some of it's stolen through here. And if there's less current going into the base, IC equals beta IB, and you turn down the current through Q1. Kind of cool. Okay. Let's see. So any other questions on this particular amplifier? I'll bring it back with the buffer at a later time. But this is again safety circuitry here. But let's go on and look at the second amplifier. If there's no questions, I don't know what, because we were about at the same place in this previous section at about the same time, at about 3:30, but then all of a sudden in 5 minutes you did an entire stage or something, and now I'm way ahead again. But all good. Okay. ST Microelectronics used to have the best data sheets. If I had two parts and one was an ST part and one was, an on part or something, I'd probably look at the ST part first just because of the data sheets being so good. They tell you more information. They've got currents on here, some other things. For today, kind of ignore the diodes and ignore the capacitor. And let's do the same thing. So really the best way to understand what this circuit is doing is to circle stages. So, and again, you could start any place you wanted to, but let's start from the input just because. So what's the first stage you see when you come in on the input? So here's the inverting input. I don't think there is a new symbol, but it looks like the more traditional current source symbol. So like we need to go there. Yeah, I don't see anything else. So assuming that these are the inputs, what's the first stage you hit?
Diff pair input.
Diff pair. Okay, so let's try to circle the whole thing. What do I circle?
Include all four of the PNPs and the
Okay.
two NPNs at the bottom.
Okay.
And the current source.
And the current source. Yes. And again, if it doesn't go rail to rail, if it doesn't go all the way up to the supply and all the way down to your lowest voltage, you probably don't have everything circled for that stage. Okay. And again, same thing as the last circuit, the last amplifier we looked at. They're using PNP based, in other words, PNP input transistors. Okay. What do you notice about the input transistors?
There's a PNP going into the base of a PNP to level shift?
Is it for level shifting? What's the job of an input stage? These do end up, you know, affecting the voltages that you can give it, but yes. So
Will
what's
that
the,
increase the Rn even more?
yes, what if I just gave you Q1 and Q2, you kind of know it as having this connected up here, but it's really the pretty much the same circuit. What do you see there?
It looks like it's a Darlington pair or something like that.
Exactly, it's a Darlington pair. So if we looked at an NPN Darlington pair, and what's this? The PNP
The
version.
Parlington pair.
So I like that. Okay, yes, this is a Darlington Parlington pair. And just to remind you, what's the Rn of a Darlington pair? Let's say just on this side. We've been
R pi 1 plus R pi 2 times 1 plus beta.
yes, R pi 2 times 1 plus beta. And if for those of you that don't see that, if you had a transistor with a resistor below it, like RE, you'd know this equation, but instead of R pi, it would be RE times 1 plus beta. But if you look at this circuit right here, the resistance below the emitter of your transistor here. So again, there's some resistance below this emitter, just like there's resistance below this emitter. But the resistance is the Rn of a transistor, which is R pi 2. So this is just acting like Re. And since it hits the base, the Re equals R pi 2. Is that good for everybody? Okay. So this has dramatically higher Rn than the previous circuit. Previous circuit, what was the Rn if you just look at one side of this circuit?
Just R pi.
Just R pi. And depending on what textbook you look at, some of them say 2 R pi, but basically R pi. Okay, so this one's much bigger. Okay. If you look at the circuit here, there's 100 microamps going through here, but only 6 microamps going through the tail current source here. So in this case, this is your ISS. S. Okay. So there's very little current going through this diff pair as compared to later stages. Why might that be? Why might you design for that? Again, think about what you like in input stages. Oh, go ahead.
Oh,
I'm sorry.
That made me reconsider. Well, I guess what I was thinking was if you're using a smaller ISS, when you change one side, there'll be less of a change in current proportionally. Like if you're using 6 milliamps or something like that, the same change would be a lot greater.
Okay.
Does that help your RN be bigger?
Yeah,
Maybe
but
still.
yeah, but how? That's exactly it.
Less change in, or
think in equations rather than touchy-feely on this one.
so a voltage over a smaller current will be a bigger resistance than a voltage over a bigger current.
Yes, and there's definitely, if you think of equation-wise, it is over a current. What's the equation of R pi?
Beta VT over IC. So a smaller IC would shoot that up a lot.
Yes. If I increase this to 100 microamps, that's like 16 times bigger. That means you'd get 1/16 of the resistance in R2. So big change. So that's another trick to increase your RN. Okay. I'm gonna go down here. Are Q1, 2, 3, 4 and the current source okay? Now, if you were using the same, let's say you had some biasing circuitry over here. And you were using it in all three of these current sources. How would you do that? How would you get less current here and more current here?
Would you just use like different size resistors?
Yes, and what's that called? Uh-oh. I think somebody got frozen. Does anybody else want to take a stab at that? How you get different currents through different current sources? I think they just lost their internet. Okay. Yeah, they're frozen. I think they lost their internet. So anybody else? Esteban, Matthew, Sanders?
Sorry, my internet was spotty too. What was the question?
Okay. So if you have just a single biasing circuit and you have three current sources here, how do you get different current through the three sources? Oh, they're back.
Sorry, our internet took it.
What happened?
Our internet went out for a while.
I shouldn't say anything, but Charter's been okay to me recently. It was going out every day, but recently it's been decent. But we're still on the question on how you get the different currents through the different current sources.
Did you hear my response or did I crash before that happened?
You crashed.
Oh, I was saying that maybe you just use different size resistors in each place.
Okay, I agree. And what are those resistors called?
Degenerate, or wait, no, they're not. Are they?
Yep. Oh. So if you drew this current source in, it would look like you'd have your VCC, if this is VCC here. There might be something written above. VCC, okay. If this is VCC, you'd have a small degeneration resistor, then you'd have a PNP. And this, you would adjust the current using your R. And this would go, this right here would go to here. And this current would be this current. Yeah, so just by picking different resistors, you can use one biasing circuit and use that bias voltage for multiple different current mirrors. Okay. Last time I think we talked about diode connecting a diff pair, didn't we? We went through the touchy-feely, or was that with somebody else?
I don't remember that. I don't think. I have to look at my notes.
Okay, so let's do that. Unless did I scroll off too quickly for anybody? Okay, all right. I'll post these. So let's see if my pen's back. Pen's back. Draw this really quick before it starts to fail again. Oh, that's not what I wanted to draw. It might have been at office hours. That's what it was. And when you diode connect one side like this, you can't use it anymore as an output. So this amplifier right here only has one output.
You talked about this in lab, I believe.
Ah,
I
okay.
think that's what you're thinking of.
Okay. I really can't remember where I say things with the Zoom interface. I don't know. I didn't realize I was such a location memory pair person. But so has everybody heard this, or just
You mention it one more time.
okay? Right. So let's start off with VI plus equals VI minus, which means, let's call this I1, I2. It means I1 equals I2, which equals ISS. So this is ISS here. Okay, so let's say that's where we start. And let's say we give this a balanced input, so that goes up by delta V and this goes down by delta V. Let's just look at the left side for a second. If I raise this side by delta V, what do you think happens to the current on the left side?
It's gonna go up exponentially.
Yes, but let's say we moved delta V so small that it's a nice little change in current. Okay. So now this current is bigger. What happens to this voltage when the current gets bigger?
It's bigger.
Goes up. Okay. So that's what's happening on the left side. That was 2 steps we got there. So that's good. Something interesting happening on the right side, because the right side just uses this voltage. It has no say in what that voltage is. This side said, hey, I'm getting more current, so I'm gonna increase my VBE. What happens to this node when VBE increases? So when the VBE on the left, left side goes up, goes lower. So this goes lower, and what happens to this VBE here?
It's bigger.
It's bigger. So both of these VBEs go up. Okay, so that's step 1. The VBE of this is going up. Let's look at what happens to the current here. If VI goes down by delta V, what happens to the current through this side?
If VI goes down, the current goes down.
Yes, so this goes down by the same delta I that the other side went up with. And now we have all of the information we need, except for that. Just looking at the left side here, And let's assume that, let's look at this equation in terms of this transistor right here. So this, what happened to the VBE of this transistor?
Went up.
Went up. But what happened to the current?
Went down.
It went down. So it has no control of VBE, and it's also, this current, this smaller current is being forced through this transistor. So something else has to change here in order to turn the current down. So what changes?
Could I guess VCE?
VCE changes. And now, you know VCE changes, but remember that VBE, a change in VBE exponentially changes the current.
Yeah.
But when you change VCE, it gets divided by 100 or 200 or something.
Okay.
So how much does VCE have to change to counteract, first of all, VBE, and then also on top of counteracting VBE, it also has to turn down IC.
A lot.
Yes. A lot. And here's your VEC if I draw it that way. But so this voltage changes a lot. This side's anchored to VCC. So this node right here moves a ton. So V out moves. If I say a ton, is that a bad way to say it?
That's good. It makes sense.
So the other question that I asked, I think in lab, is right here I diode connected it. If instead of diode connecting it, I just put a DC voltage on it. So sorry if somebody's still writing, I'll go back in a second. But let's say instead of so my question is, does this circuit have higher gain? Or does the diode connected one have higher gain?
The DC has higher gain.
So let's reason through it again here real quick. I think we have a few minutes. Yeah. Okay. So let's do the same thing. Oh, pen stopped working. Okay. Let's do a plus delta V. And you know what happens to the current now? So current went up. This side still has to accommodate that bigger current. So what does it do? This side turned up its voltage. That means it turns up its current here.
VCE goes up.
VCE goes up. So in this case, I guess properly I should say the magnitude. I'm giving you bad habits here by just dropping signs randomly. But yeah, VCE goes up. Does the base voltage change? No, because it's externally biased. It's DC. So now the VBE on this side doesn't change. And the question is, now on this side, does VCE change more or less than this circuit?
Less.
Less. And why is it less than this circuit?
VCE doesn't have to move as much in order to counteract a changing VBE. So, yeah.
Yeah, this one had to, the current was getting turned down and the VBE was getting turned up. So it had to counteract both of those. But over here, VBE is staying constant, so it doesn't have to counteract that. It just has to make IC smaller. So yeah, and this is in some of your sections, not in my section, I don't think, because it's I'm still discussing with other lab people, but there's a chip called the LM13700, and it uses this technique here. It changes VBE in if you've got less current going through a branch, it actually turns up VBE. So now VCE has to fight both VBE change and the current change. If you turn the current down, no, if you turn the current up, then it turns VBE down. If you turn the current down, it turns VBE up on this side. And that makes VCE have to work harder. And it gives you better gain. So that's what the LM13700 looks like. And we'll actually do the LM13700 in class in one of these practices. I'll bring in a op amp every day, and we'll practice this more and more on more and more complicated circuits, and you'll get faster and faster. So any questions on today? We're going to start frequency response on Friday. Right, that's all I got. Questions?
Thank you, Professor.
Do you want to see the video so far?
I would love to, but we have to go take an exam right now.
Oh, that's right. That's right. I forgot. You just told me that too. I'm sorry.
I did?
Good luck. Okay. Is that, who is that?
Tristan said that he was the one that said that. I guess. I don't know. I'm getting delusional.
Right.
Okay, have a good rest of your day.
Right. Bye-bye.